let us see the fifth problem. Fifth problem statement is as follows. Determine the impulse response h of n of a discrete time ideal low pass filter whose frequency response h of e to the power of j omega is given by. Okay. So, this is what is given to us, this is the response, and I have to calculate what is impulse response. That means, I have to calculate what is h of n given h of e to the power of j omega, that is frequency response is given, we have to find out the impulse response. Now, as we know, to solve this type of problems, we should calculate the inverse of DTFT, that is inverse of discrete time Fourier transform. So, we apply that formula here and let us find out what is h of n for such a ideal low pass filter. Okay. So, let us do it here. Now, I have to calculate what is h of n. h of n is inverse discrete time Fourier transform of h of e to the power of j omega. Okay. The formula for this is given by 1 by 2 pi integral minus pi to plus pi, okay, h of e to the power of j omega, okay, e to the power of j omega d omega. Okay. So, this is the formula. Okay. Let us see this, h of n is equal to 1 by 2 pi integral minus pi to plus pi h of e to the power of j omega e to the power of j omega n d omega. So, this is the formula. So, earlier sentence you replace with this sentence. So, now let us calculate what is the answer for this. Now, looking at the ideal low pass filter, if you see here, okay, it is existing from minus omega c to plus omega c. So, let us change the limits here. So, what I will do is I will write like this 1 by 2 pi, okay, it is minus omega c to plus omega c here, and what is h of e j omega? 1 into e to the power of j omega n d omega. Okay. So, let us integrate this. When I integrate this, I will get like this. So, this is 1 by 2 pi, okay, into 1 by j n, okay, e to the power of j omega n minus omega c to plus omega c. Okay. So, let us do it here. So, this I can write as this is equal to 1 by, let us take everything here 2 pi j n, okay, and this will be e to the power of j omega c n minus e to the power of minus j omega c n. Okay, we have just substituted these limits here. So, what I will get is what I will do is I will keep pi n here outside and then e to the power of j omega c n minus e to the power of j omega c n by 2 j. As you see here, this is a sine function. So, I can write this as h of n is equal to, this is sine omega c n by pi n. So, this is our impulse response for a given ideal low pass filter with a frequency response which is given. So, this is our impulse response. Let us see the question number 6. Question number 6 is, a discrete time signal is given as x of n is equal to a to the power of n u of n, where mod a is less than 1. Now, we have to determine the energy density spectrum phi of e to the power of j omega. So, let us see what is what are the steps involved. Let us see what are the steps involved in doing this type of problems. Okay. So, let us write down what is given to us. Okay. X of n is given as a to the power of n u of n, okay, and then we have to calculate the DTFT of this. So, x e to the power of j omega is nothing but DTFT of x of n, okay. X of e to the power of j omega is discrete time Fourier transform of x of n, that is given by summation of n is equal to minus infinity to plus infinity x of n e to the power of minus j omega n. Now, let us see what are the values given to us. As you see here, this is u of n. So, what we have to do is let us substitute those values here. So, let us put n is equal to 0 to infinity, because this is a right handed sequence. This is a to the power of n e to the power of minus j omega n. Now, let us take out n as common. So, this is equal to n is equal to 0, then this I can write as a e to the power of minus j omega whole to the power of n. So, as you are aware, this is nothing but equal to 1 by 1 minus a to the power of minus j omega. Okay. So, this is the x of n for us. Now, how do I calculate the energy spectral density? As you are aware, the energy spectral density is given by whole square. That means, I know what is x of n for us. Now, we know what this is our xc of e to the power of j omega. So, let us multiply this. So, then I will get this as 1 by 1 minus a e to the power of minus j omega into 1 by 1 minus a e to the power of j omega. So, let us calculate this, then I will get so this I can write as 1 by 1 minus a e to the power of j omega plus e to the power of minus j omega plus a square. Okay, as you see here, this is a cos omega. What is missing is 2. So, I can write this equation as psi of e to the power of j omega is equal to 1 by 1 minus 2a cos omega plus a square. So, this is our energy spectral density given by 1 by 1 minus 2a cos omega plus a square. Now, let us see question number 7. We have to find out the discrete time Fourier transform of a x of n is equal to u of n. Let us see this. Okay. What is given? X of n is given as 1 when n is greater than or equal to 0 and 0 when n is less than 0. This is what is given. Now, we have to calculate what is x e to the power of j omega, that is the discrete time Fourier transform of x of n. So, let us write down that. So, x of e to the power of j omega is equal to dtft of this and is given by n is equal to minus infinity to plus infinity x of n e to the power of minus j omega n. So, for us our limits are known. Okay, this exists only on the right hand side. So, it will be n is equal to 0 to infinity. Then what is x of n for us? X of n is 1. So, we will put 1 here, e to the power of minus j omega n. Okay. So, now we have to identify what is the summation results in. So, we know one formula, that is a summation of series is like this: n is equal to n1 to n2, okay, a to the power of n. So, when I do this summation, this type of summation, this is given by a to the power of n1 minus a to the power of n2 plus 1 by 1 minus a. Okay, let us put that here. So, what I will get is, that is e to the power of minus j omega 0 minus e to the power of minus j omega infinity, because infinity plus 1 is again infinity, by 1 minus a for us is e to the power of minus j omega n. So, this is in fact equal to 1 by 1 minus e to the power of minus j omega n. This is my x of e to the power of j omega. So, this is the, that means any u of n given like this, the discrete time Fourier transform such a function is given by 1 by 1 minus e to the power of minus j omega n. Let us see question number 8. Question number 8 is, we have to find the frequency response and impulse response of a causal discrete time LTI system, which is characterized by the difference equation given like this. Okay, so what is given? This is what is given. I have to calculate what is the frequency response and also what is the impulse response. But we know the frequency response is nothing but h of e to the power of j omega. So, I have to calculate this, and also what is impulse response? Impulse response h of n. So, once I know the frequency response, I can calculate the inverse discrete time Fourier transform for that, then I will get the impulse response. So, let us calculate first what is h of e to the power of j omega, that is a frequency response, and given the frequency response, I will calculate what is the impulse response. Let us start this. Now, let us say y of n is having a discrete time Fourier transform of y of e to the power of j omega. Okay. Then x of n is having a discrete time Fourier transform of x of e to the power of j omega. Okay. Now, with this knowledge, let us calculate this problem. So, what is given? Let us say this is, I have to calculate the dTft of this. First of all, y of n minus a y of n minus 1, okay, discrete time Fourier transform of x of n. Okay. dTft of y of n is what? Y of e to the power of j omega. So, let us write down that first, y of e to the power of j omega. This is the dTft of this, minus a y of e to the power of j omega. Okay. This is a time shifting function. So, I can write this as minus j omega. Okay. This is equal to x of e to the power of j omega. Now, I will take y of e to the power of j omega common. So, this is y of e to the power of j omega. I will take it as common. So, this will be 1 minus a e to the power of minus j omega. Okay. So, this is equal to x of e to the power of j omega. Now, let us write down what is y by x. Okay. So, we can write it here. So, y of e to the power of j omega by x of e to the power of j omega is equal to how much? That will be equal to 1 by 1 minus a e to the power of minus j omega. So, what is this? Y is the output and x is the input. So, ratio of this is nothing but your transfer function which is in frequency domain. So, we call this as a frequency response. So, this is nothing but equal to h of e to the power of j omega. This is equal to 1 by 1 minus a e to the power of minus j omega. So, this is my frequency response. Now, what is the next we have to calculate? We have to calculate what is the impulse response or what is the impulse response, that is h of n we have to calculate now. So, let us just take out that. If I take the inverse dTft of this, I will get h of n. So, h of n is nothing but inverse discrete time Fourier transform of h of e to the power of j omega. So, this is equal to 1 by 1 minus a e to the power of minus j omega. So, this is nothing but equal to a to the power of n u of n. This is my h of n. This is my impulse response. Let us see some few important points in dTft before we actually wind this up session on dTft. Some of the few points we will just summarize here. The first point is the dTft is always periodic with a period 1 in the frequency domain or period 2 pi in the ohm domain. That means, in a continuation domain the period is 1, whereas in the discrete time it is 2 pi, that is the dTft. So, this is always periodic. That is one important point which you should understand in the case of dTft. The second important point is, the more a signal is localized in one domain, that is time or frequency, the less it is localized in the other domain. That means, if you find a signal which is localized, okay, in one domain, that can be either time or frequency domain, then when I convert this into another transform, it is less likely to be localized. That is the second important point of a discrete time Fourier transforms. Okay, then the third point is, as a consequence of the periodicity and the frequency shifting properties of the dTft, there exists a special relationship between the ideal low pass filter and the ideal high pass discrete time filter. Now, if we look at the properties of a dTft, one property we have seen that it is periodic in nature, and combined with this the frequency shifting property, we can establish a relationship between an ideal low pass filter and a discrete time high pass filter. So, there can be a relationship exist which can be established between these two types of filters, because the fact that dTft is periodic in nature and also taking into cognizance the property of frequency shifting in dTft. I can establish a relationship between an ideal low pass filter with a high pass filter which is in discrete time filter. The next point is convolution and multiplication of functions at dual operations in the time and frequency domains. This has been, we have been looking at this type of property since long. That means, whenever x1 and x2 of n are convolved in time domain, in frequency domain it is multiplication or vice versa. This is one of the important properties of convolution. given the Fourier transform of a sequence, it is possible to use Fourier transform properties to determine whether a particular sequence has a number of different properties. That means whenever I find out the Fourier transform of a sequence and we find out its properties, then we can also find out what are the different other properties which can exist by analyzing the Fourier transform properties. Okay, the another important point here is Parsevals relation states that the energy can also be determined integrating the energy per unit frequency, that is x of e to the power of j omega whole square by 2 pi over a full 2 pi interval of distinct discrete time frequencies. That is the next property. So what does it say? It says that Parsevals relation states that this energy can also be determined by integrating the energy per unit frequency. Okay, for us, what is the periodic? Period is 2 pi. So x of e to the power of j omega whole square gives us the energy spectral density. When I calculate per 2 pi over a full 2 pi interval of a distinct discrete time frequencies. That's the next property. In addition to all these properties, the duality for the discrete Fourier series, there is a duality between the discrete time Fourier transform and the continuous time Fourier series. It's again a very important property. There is a duality that exists between the discrete time Fourier transform and the continuous time Fourier series. So DTFT and CTFS have a duality relationship between them. Next property, as in the continuous time case, discrete time periodic signals can be incorporated within the framework of the DTFT by interpreting the transform of a period signal as an impulse train in the frequency domain. So take a continuous time case that is transformed into a impulse train. Okay, when you do this, this is the relationship that can be established. That is, a continuous time case, discrete time periodic signals can be incorporated within the framework of the DTFT by interpreting the transform of a period signal as an impulse train in the frequency domain. So, have a train of impulse functions. Next, an LTI system is stable, then its impulse response is also stable. So, when I calculate its frequency response, that is also stable because impulse response is summable, okay, absolutely summable. Therefore, what happens? The frequency response is also convergent, that is also stable. Okay, these are some of the few important points we have summarized just for DTFT. Remember these points because once we start discussing a next topic called as discrete Fourier transforms, then we'll try to find out what are the limitations of DTFT, then we'll get transferred into a discrete Fourier transform. We'll see the difference between these two.